In section 2 of chapter 8, we are going to be simplifying complex values that will help us initialize our investigation into complex numbers. So, let's do this. First, I want to review a concept that, again, feels like a no-brainer duh statement, but it's going to unlock the ability for us to start investigating more complex ideas. Problem number 1, I have the square root of 3 times the square root of 3. I'm sure all of you realize that answer is just 3. But what's more important is I want to make sure that you understand why. That's because this is the same thing as the square root of 3 times itself, or the square root of 3 squared. The reason that's important is because the square root and the square undo one another, which is why the answer to this is just 3. The square root of 14 times the square root of 14 could be rewritten as the quantity of the square root of 14 quantity squared. And again, the square root and the square undo one another, which is why the answer to this is just 14. It even works with fractions. The square root of 7 over 4 times the square root of 7 over 4 is the same thing as the quantity of the square root of 7 over 4 quantity squared. The square root and the square undo one another, which is why the answer to this is 7 over 4. And heck, it even works with decimals. The square root of 7.8 times the square root of 7.8 is equal to the quantity of the square root of 7.8 quantity squared, where the square root and the square undo one another because they are inverse operations, and the answer is 7.8. Yay. This seems, at face level value, something that's just a no-duh statement. But as soon as I make this more complex, it tends to baffle some students in its initial investigation. Because what I'm going to start with is we're going to be solving or simplifying complex values with I, because here's a rule for y'all. I is not allowed to have exponents. I to the second power, you cannot write that as an answer in this class. I to the third power, no go. I to the fourth, can't do it. I to the fifth, nope. I can never have an exponent, and here's why. I'm going to start first with a statement from the previous lesson that again is going to feel like a duh statement, but it's really, really important for what we're about to do. I to the first power is just the square root of -1, which is equal to I. We are going to formulate the rest of our understanding of complex values with exponents based off of that information. Because the next thing I'm going to do is I'm going to find I to the second power. Well, that's just the square root of -1 times the square root of -1. And according to what we just got done doing, if you ever multiply a square root times itself, it's equal to the value underneath it. And then we're going to move on to I to the third power. I'm going to define I to the third power with I to the first and I to the second, because I to the third is just I to the second times I to the first. And I already found out on those previous two steps what those are. I to the second power is -1. I to the first power is just I, which is why this is equal to -I. So if you ever see a I to the third power in a problem, you can just turn it into -I. Then we're going to do I to the fourth power. And that's going to be equal to I to the second power times I to the second power, which is equal to -1 times -1. Therefore, I to the fourth power is just 1. So this idea is incredibly, incredibly important. But I'm not going to stop there. I want to figure out what I to the fifth power is. I to the fifth power, I could write as I to the fourth times I to the first. But I already know what I to the fourth power is. I to the fourth power is just equal to 1. So this just turns into a 1. 1 times I to the first is just I to the first. That's just I. I wonder what I to the fourth power is. Sorry, not fourth, sorry. I to the sixth power. That is I to the fourth times I to the second. And again, I already know what I to the fourth power is. That's 1. Therefore, this is just going to turn into I to the second power, which I also know is just negative 1. Let's try I to the seventh power. That's just I to the fourth times I to the third. But I already know what I to the fourth is. That's just 1. So it's 1 times I to the third, which I know is equal to negative I. So this is negative I. I wonder what I to the 8th power is. Hopefully you're starting to pick up on a pattern. That's just 1. That's just 1. Last I checked, 1 times 1 is equal to 1. I wonder what I to the 9th power is. That's just equal to I to the 4th times I to the 4th times I to the 1st. This is going to turn to 1. That's going to turn into 1. I to the 1st is just I. I to the 10th is I to the 4th times I to the 4th times I to the 2nd. The I to the 4ths go away. I to the 2nd is negative 1. I to the 11th, I am being repetitive for a very, very specific reason. I want you to see the pattern. I want you to see what I'm doing so you can understand that this is just going to go through a cycle. But that's going to be really, really important for the number I'm going to do after this. So right now it might feel like, oh, this is just really, really redundant, Mr. Silva. I don't want to do this because this is all ones. But now I'm going to show you a different problem. I to the 237th. Now what you could do, hopefully you realize that this is just going through this sequence over and over again. First power, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12. What I don't want you to do is count this pattern until you get to 237. That's going to take way too long. I mean, you could do it if you got like a spare like 10 minutes to do a single problem. But seeing as how I'm giving you like 30 to do, that's not going to be very conducive to your time. What we're attempting to do is to see how many cycles of 4 we can go through. We're trying to break it into groups of 4. That's the definition of division. You have a number, you're trying to break it into groups of 4. All I'm really doing is I'm trying to see how many times does 4 go into this. Whatever the remainder is, that'll tell you where you are in the sequence. If you have a remainder of 1, then your answer will be I. If you have a remainder of 2, the answer would be negative 1. If you have a remainder of 3, the answer would be negative I. But here's the kicker. If there is no remainder, that means 4 goes into it nicely. That's where it's this category. This is when there is no remainder. That has an answer of 1. So what we need to do is take the 237 and divide it by 4. 4 does not go into 2 nicely. But 4 does go into 23 if I multiply it by 5. 5 times 4 is 20. Subtract 20, I'll get a 3. Bring down the next term, which is 7. Then I ask myself, how many times does 4 go into 37 without going over? It goes into it 9 times. That's going to give me a 36. My remainder is 1. Therefore, it falls under this first category, which means the answer to this is I. Again, that's all fun and dandy. But as soon as I start making that exponent really, really, really large, you're going to start hating me again because you're not going to want to do long division on a really, really long problem. All right, let's use technology instead. If you divide a number by 4, if the remainder is 1, that means the answer is 59 on a calculator, 0.25. If the remainder is 0.25 at the end of the division, that means it's this. If you have a remainder of 2, then through the division process on a calculator, you'll have a remainder of 0.5, that'll be this is your answer. If the remainder is 0.75 at the end of your decimal, then this is your answer. If it goes into it nicely, this is your answer. All you need is a calculator and like 3 seconds to solve these problems. Problem number 1, all I got to do is take that 21 and divide it by 4. That will be equal to 5.25. Because this ends in a 0.25, that tells me that the remainder is 1. That means it's going to be the first term in that cycle. That means that the answer is I. 57. I'm going to divide that by 4 in the second problem. And that's going to be equal to 14.25. Again, all I care about is the decimal. The remainder is 0.25. That means it had a remainder, if I use long division, of 1. Therefore, it's going to be the first pattern in the cycle. I'm going to take the 113, divide it by 4. And I'm going to get 28.25. Man, I chose a bunch of problems that all end in 0.25. The remainder is 0.25. That means it's the first number in the cycle. That means the answer is I. This one doesn't end in 0.25. 276 divided by 4. Is equal to 69.0. The remainder is 0. That means it's going to be the fourth part of the pattern, which is just equal to 1. For i's, we treat them like variables. That means if you have two terms being added or subtracted to one another, you can only combine them together through subtraction and addition if they have I. So for problem 1, I have a 5i plus 7i. 5 plus 7 is 12, so this is 12i. No big deal. Problem 2, I have a 2ix. This will only combine together with something that has an I and an x. This has an ix, so these two can combine together. But the third term only has an x, so it will remain by itself when I add the first two terms together. So I'll get negative 3ix plus 7x as my final answer. But the big one that I want to point out is problem 3 and 4. It's important for you to recognize I, by definition, is the square root of negative 1. Therefore, I is a radical. Problem number 3, I'm not okay with that. I can't have an I in the denominator because we're not allowed radicals in the denominator. So I need to get rid of that complex number in the denominator. I namely need to get rid of the I. The way we do that is by turning it into an I squared. I'm going to multiply top and bottom by I. That'll give me 7i over negative 3i squared. That is equal to 7i over 3, because I squared is negative 1. But then problems like number 4 are a little different. When you have a binomial, you have to recall what we did earlier in the year. You have to multiply by the conjugate. I'm going to multiply top and bottom by 5 minus 6i over 5 minus 6i. When I multiply out the numerator, I'll get negative 10 plus 12i. But for the denominator, whenever you multiply a binomial by its conjugate, it just turns into the first term squared, which is 25, minus the second term squared, which is 6i squared. That is going to be equal to negative 10 plus 12i over 25 plus 6, which is why our final answer is negative 10 plus 12i over 31. Oh, wait, no, that's wrong. Because this should be 6 squared. That should be a 36. Which is not going to give me a 31. That's going to give me a 61. There we go.